Hey guys, so this is section 7.4 of the law of corresponding states. So we have seen the ideal gas law, we've seen the van der Waals equation, the Waals equation. Our goal here is to see if we can come up with an equation of state that whose variables do not depend upon the molecule, like there's the A and B in Waals and van der Waals, like that. To get an equation without those. So let's see what happens. What we're going to do is define reduced variables, temperature, pressure, and volume. So T sub R stands for reduced temperature, and it's just equal to whatever the temperature of the gas is divided by its critical temperature. We saw this before, the critical temperature. Likewise, the reduced pressure is the pressure divided by the critical pressure. And the reduced molar volume is the actual molar volume divided by the critical molar volume. So because molecules at their critical state are going to behave pretty similarly, it makes sense that if the ratio of the temperature to the critical temperature and the pressure to the critical pressure, etc., is the same for two molecules, then which means that their reduced temperature, pressure, and volume are similar, then we'd expect those molecules to behave similarly under those conditions. For example, if we look at ethanol and ethane, these are their critical temperatures, pressures, and molar volumes. If we take ethanol under these conditions, 298.15 Kelvin, 3.14 bar, 2.790 liters, we can calculate the reduced temperature, pressure, and volume, which are over here. Just 298.15 divided by 513.92 for the reduced temperature, etc. So what we're saying is that the law of corresponding states says that if ethane's reduced variables are the same value, then it's going to behave in a similar manner to ethanol under these conditions. It ends up that they both have the same reduced temperature when ethane has its temperature 177.13 Kelvin, now ethanol 298.15. Likewise, this pressure for ethane and this pressure for ethanol give the same reduced pressure of this. You should check my math, guys. And also likewise for the volume. So that says that under these conditions, because they have the same reduced variables, temperature, pressure, and volume, we expect them to behave similarly. They are in corresponding states. So now let's look at the van der Waals equation. There's one form of the van der Waals using the molar volume, so n isn't there because it's 1. We can rewrite this in terms of the reduced variables, because remember, the reduced temperature, reduced pressure is the pressure over the critical pressure. So if we rearrange this, solve for the pressure, it's just the reduced pressure times the critical pressure, and the same thing for temperature and volume. So what we're doing in here is we're substituting for pressure the reduced pressure times the critical pressure. Likewise, temperature, volume, and volume. But we showed back in section 7.2 that the critical pressure for the van der Waals equation can be written like this, the molar volume like this, and the critical temperature like this. Substituting these values in for the critical pressure, volume, and temperature, we get this. There's the pressure, temperature, volume, so on. This reduces really nicely, so check my algebra, but it looks like everything cancels here till we get down to this really simple equation. The nice thing about this equation, guys, is that this is the van der Waals equation without any of the van der Waals constants, A or B. However, it doesn't really do what we wanted to, because we wanted to get an equation that didn't matter which gas, that was independent of the gas, of the molecule. This is not, because we still need to look up the critical pressure, temperature, and volume for this specific gas. So what this graph is this is showing graphing the compression factor, Z, versus the reduced pressure. And each of these different colored spheres is for a different gas, and each of these lines is at a different reduced temperature. So reduced temperature is 2, 1.5, 1.32, and so on. These are the gases over here. And what it shows is that they have under the, when the reduced variables are the same, they have very similar properties. So the same reduced temperature and pressure gives very similar values for the compression factor. Remember, compression factor, it's a handy measure of how similar to an ideal gas gas is behaving. Now, it ends up that the law of corresponding states works best if we're talking about molecules that are not polar, don't have a dipole, that they're more or less spherical. Because it ends up that if they're polar, then the intermolecular potential of that molecule with other molecules depends upon its orientation, and that's not taken into account in the law of corresponding states. So one thing we can do with the law of corresponding states is to estimate Z, the compression factor for a gas at some reduced pressure and temperature. These lines here are for different, each line represents a different reduced temperature. It's graphing compression factor versus reduced pressure for that temperature. And this is from the van der Waals equation. So one way we can use the law of corresponding states, which is what gives us these graphs, is the percent error. So the percent error, it tells us what error we would have by treating that gas as an ideal gas. In other words, how different does that gas behave than an ideal gas would under those conditions. So the difference between the compression factor minus 1, which is if it's an ideal gas, the compression factor is 1, divided by the Z times 100. So, for example, when we look at the reduced temperature and pressure both being 1, if we go over to this graph right here, the reduced pressure is 1 right here, and the reduced temperature is 1 right down here. So if we go over, we read the compression factor Z. I got about 0.3 or something like that. So that tells us that the percent error is going to be about negative 230%, which is huge, which means it's, ideal gas is basically useless under those conditions. However, if we go up to a reduced temperature of 2, which is this line right here, at a reduced pressure of 2 right here, I get a value of about 0.88 or so for the compression factor. Plugging that in, we see that that gives us a percent error of negative 14%. That's not too bad, especially compared to like negative 230. All right, so in this example, we're going to calculate the volume occupied by this much ammonia gas at this temperature and this pressure, and calculate the percent error that we would get if the volume were calculated using the ideal gas law. So you'll need to know the critical temperature and pressure for ammonia, which are right here. I'll give you to them. So we're going to calculate first the reduced pressure, the pressure over the critical pressure. I get 1.58. Same thing for the reduced temperature. I get 1.30. Knowing these two values, we go over to our graph, and the reduced pressure was 1.58. I got that as about right here. The reduced temperature was 1.3, so this isotherm right here. So if we go over and read the compression factor, I read it as about 0.61 or something like that. So remember, Z is PV over nRT. If this is an ideal gas, then it's 1. If it's not, it's other than 1. So we got Z is 0.61. So we rearrange this equation, solve for the volume, get Z times nRT over P, which gives us about 4 liters. That's what the van der Waals equation basically says the volume would be of that gas under these conditions, that much gas. If we use the ideal gas law, it's just, remember, the volume is the compression factor times the ideal volume. So the ideal volume is just that volume over Z, which gives us like 6.6 liters, percent error of like 64%, which is pretty big. Okay. Now we can also get an expression for the critical compression factor, ZC, for a van der Waals gas. So Z is PV over RT. For molar volume is V molar. So critical compression factor would just be when these values that are at their critical values. But once more, we showed back in section 7.2 that for a van der Waals gas, we can write the critical pressure, molar volume, and temperature like this. Plugging these values in here for these three, it ends up, it just simplifies to 3/8. What does that say? That says that this predicts that the compression factor, the critical compression factor for all gases should be the same, regardless of the gas. If you do a similar analysis with the Redlich-Kwong equation, it gives you a factor of the critical compression factor of 0.333, a little bit less than 3/8. And you can look these up. You can look up the critical compression factors. Table 7.2 in the back of your text does so. And when you look at it, they're all like 0.29, 0.3. Really, so first of all, they're all very close to being the same, which means qualitatively the prediction is good. Quantitatively, they're a little bit off. Redlich-Kwong is closer than the van der Waals is, but still not too bad.